Impacts of carbon capture and sequestration. Hello there, my name is Professor Carbon. Today, I'm going to be talking to you about carbon capture and sequestration. Firstly, I'll be providing some background information on CO2. Then, I'll explain the need for negative emission technologies. So, why capture and store carbon? Well, to best explain this, perhaps we need to start by explaining what exactly carbon is and the impact that it has on the Earth's climate system. Carbon dioxide is one of the greenhouse gases that plays a vital role in the Earth's climate system. These gases are located in the atmosphere and both absorb and emit infrared radiation from the sun. The more gases in the atmosphere, the less radiation leaks through and emits back into space, leading to an increased surface temperature. An increase in the Earth's surface temperature can have negative impacts, such as an increase in sea height due to the melting ice caps, an increased volatility of rainfall leading to food supply and water destabilization, an increase in powerful hurricanes, drought, and the acidification of seawater, posing major threats to marine ecosystems. So what are we doing about it? On December 12, 2015, members of the United Nations Framework Convention on Climate Change reached a decision known as the Paris Agreement. In this agreement, nations agreed to set a personal carbon budget that would keep the global temperature rise below 2 degrees Celsius within this century. And how's that going? Well, not so good. The following chart projects the required carbon emissions to meet our target of 2 degrees by the year 2100. Without negative emission technology, this is unattainable. This is where carbon capture and sequestration comes in. Carbon capture is the process of separating CO2 from the air, product streams, or fuels so that it can be later sequestered. There are many different carbon capture technologies. This presentation specifically touches on technologies focused on combustion processes. The three main types of combustion carbon capturing are post-combustion, pre-combustion, and oxy fuel combustion. The gas coming out of a combustion process contains CO2, nitrous oxides, water vapor, and some other gases. The gas is then added to a chemical absorber where just the CO2 is absorbed and the other gases are released back into the environment. This solution then has superheated steam pass through it, which releases the CO2 where it can be transported off to be stored, and the absorbent can be reused. Pre-combustion carbon capture involves treating a fuel, often coal, before it is burnt. The fuel is put into a reactor to get carbon monoxide and hydrogen gas. The carbon monoxide is then reacted with steam to produce CO2 and even more H2. This CO2 can then be absorbed in the same process as the last. The H2 gas can then be combusted as fuel and produces only water vapor. An oxy fuel combustion system uses pure oxygen instead of atmospheric air in the combustion process. This removes the nitrogen and other gases from the reaction product. The outcoming flue gas is approximately 80% CO2 by volume. The remaining portion is mainly water vapor, which can be easily removed. Electricity plant equipped with pre- or post-combustion carbon capture technology will require between 10 to 40% more energy than one without it. This is energy needed to run the equipment to remove the CO2. Accounting for this increase means that the net amount of CO2 captured is approximately 80 to 90%. Alternatively, an oxy fuel system is able to capture almost 100% of the CO2, but the additional systems for removing nitrogen and sulfur lowers this value to roughly 90%. Hey guys, so there are many different options for the storage of carbon dioxide. These can be geological storage, ocean sequestration, and mineral carbonization. Geological storage can be split into three components. Let's check it out.
The first method is enriched oil recovery. In this method, CO2 is pumped into declining oil fields to increase the amount of oil that is recoverable. Here, we have deep saline reservoirs. These are deep saltwater deposits that when mixed with CO2 form solids that cannot leach to the surface. Lastly, we have a method where coal that is too costly or difficult to mine can be used for carbon storage. Now let's go check out ocean sequestration. Here, CO2 can be piped deep into the ocean where it will remain a liquid. Isolated from the atmosphere, it will solidify and be trapped.
Hey guys, welcome back. Wrapping it all up, let's take a look at the following data. Currently, 21 CCS facilities capture 37 million tons of CO2 annually, with 220 million tons already stored. To reach current climate goals from the Paris Agreement, 2,500 CCS facilities with the capacity of 1.5 megatons per year will need to be operating in 2040, assuming that 14% of emission reductions are from CCS. Thanks for listening, guys. I hope that you enjoyed the presentation and now understand the necessity of CCS technologies moving forward into our future. Bye for now.